Wait. Okay. We can go. There he is.
Yeah.
Hey, Burhan. We just started 1 second ago. Welcome. All right. Go ahead, Naveed.
Okay, so today we are going to be talking about neural networks. Um, I'll try to provide you the motivation behind why researchers started looking into neural networks, what was the motivation behind that, and then we'll talk about why they have shown this impressive performance just now. Why not earlier? Because they existed since 80s. Um, and then we'll build from there how to I'll try to give you a mathematical background of it, and then finally we'll talk about forward pass and then backward pass. We'll talk about activation functions and stuff. I have created these notes for myself because it's a lengthy topic, so I'll be looking into my notes. But before I begin, can anyone tell me what do you know about neural networks, Ron or Vector or even James?
The only thing I know about neural networks is that they are used for um, large language models like ChatGPT. That's the only thing I know about them. So I knew like they
Yeah.
handle like a lot of complex stuff behind the scene.
Uh-huh.
I have a rough idea, but it's like maybe trying to replicate how human brain functions. Maybe I heard it's somewhere, so it's like
Mm-hmm.
closer to how human process stuff.
Okay, James.
The way I think about a neural network, I don't know if this is the right way to think about it, but I think about it. There's layers, and then there's layers of linear transformations, and then in between them, there's these nonlinear activation functions, and then that allows you to make something that can shape itself around very nonlinear types of functions.
Yeah, that's a very good technical definition of it. Um, let's see. So let's first talk about the motivation behind neural networks. So of course, as the name suggests, these are biologically inspired. What we have inside our brains, the biological neural networks, they're inspired from them. But of course, even though these are inspired from them, you cannot say this is what happens inside our brain for the simple reason that neuroscientists um, say they don't know anything about how the brain works, or they know very little about how the brain works. So, saying that we have replicated that inside a computer would be a very would be exaggeration of what happens. But still, the idea is inspired from there. So let's see. Let me begin the discussion with how a biological neuron looks like. So the basic building block of a neural network is called a neuron, and this is what a biological neuron looks like. So you have this weird looking structure like this, then we have this tube, and then finally something like this. This is a diagram that you'd usually see inside biology books. This is usually called the nucleus of a neuron cell. These are called dendrites, and these are called the axons. So what happens is this is just one neuron. This is occurring in close proximity of millions of other neurons. The way neural networks process stuff is that they take inputs using these what are called these dendrites. So you can consider them as the input. Once they take the input, there's some processing that happens inside the nucleus, and then they produce an output, which is then passed through this tube towards these what are called these axons, which can be considered as the output. And then this output is connected to the input of another neuron cell. So you can consider it as there's another these are another dendrites which then takes the input from it, process them again, and then passes the output to another neuron cell, and so on. So data comes in, it gets processed inside the nucleus, then an output is produced, and then that output is transmitted to other neurons. This is what typically happens. Now, so so the inspiration is taken from here. What a this is a biological neuron. What happens inside a artificial neuron, which is sometimes called the perceptron, something similar happens. So what we'll be doing is we'll take some input data, which would be in the form of a vector. You can call it x. We'll take that input. We'll do some processing on it. Let's just I'm writing here p, which means processing, and then whatever processing we do on it, this will be producing an output, and then that output we can. So this is a single perceptron. What we can do is then combine multiple of these. So we can add another neuron cell here, where the output from the previous neuron is fed into the input of this second neuron or perceptron, and we can add lots of them in series, or we can also add them in parallel. This is what would typically happen. Um, so the question is if they so this is the basic algorithm. Question is how does it what is the intuition behind like how w- it performs something that better than what other algorithms were doing. So for that, let's take an example case where we have, let's say, some features um, of. So the problem that we're looking into is there's a T-shirt or any item for that matter, and we want to see h- what is going to be the probability of this T-shirt or this item to be a top seller in a market. So the features that we are having for that is, let's say, the price of this item, and then we have, let's say, the shipping cost, and then marketing, like how have we done the marketing for it, and then what material is it made of. Yeah, so these are the features. We want to make use of them to predict the probability um, of it being a top seller, right? So what would happen if we would like to do to solve this problem? So it's a obviously it's a classification problem because the probability the output is going to be between 0 and 1. So if it is 0, it just simply means it's not going to be a top seller. If it is 1, it means it's going to be a top seller. um, what we can do is use a logistic regression in order to do that, which would take these raw features as an input and then produce an output based on these features. That we can do that. But if you ask a person, an expert in these things, he tell you that although these are the raw features, the price, shipping cost, marketing, and material, but these do not directly affect or the probability if it's going to be a top seller. We have some factors which are going to be contributing to that, and those factors depend on these things. So they are not directly related to the probability, but rather they make up some other factors which are then going to be affecting the probability. Let's say those factors are, so let's write them. What could be the factors that could affect the probability? So one of the factor could be the affordability. Is this shirt affordable? Affordable. Another factor could be, are people aware of it being present in the market? Another factor could be the perceived quality What happened? Perceived quality. So these are going to be the factors that are going to impact the probability if it is going to be a top seller or not. So if you use a logistic regression, they won't take care, like they won't be looking into these. They would just directly take the inputs, these raw features, and predict the probability from it. What we want to do is not to use them directly, but combine them in certain ways which could then make more useful features such as these factors: affordability, awareness, perceived quality, and so on, which would be more better or more easier for the algorithm than to predict if it's going to be a top seller or not. What can contribute towards the affordability? So price is one feature that can um, impact this, and shipping cost is another one. Together, these two make the total cost, which determines if it's affordable or not. Awareness is, of course, directly related to the marketing. So if the marketing is done well, we know that people are going to be aware of this thing being present. Perceived quality depends upon the price and the material. So if you if someone would like to guess if this stuff that I'm looking into, if it's of high quality, people would usually check the material of it, what it is made of, and then they'd also see if the price is high. They think that, of course, if the price is high, it means it's something of high value. So the perceived quality depends on these two. So as you can see, these features, raw features, are combined in certain intelligent ways which determines these factors, and then those factors finally impact the probability of this shirt being a top seller or not. Does this make sense? Whatever I'm saying.
Yeah.
Yes, it does.
Great. So the reason we cannot use logistic regression here is because it would take these and won't account for this. We need to come up with an algorithm which would take these raw features, combine them in certain ways, such that they would look for even more valuable factors which could contribute to the final outcome, which would be more decisive in determining if it's going to be a top seller or not. And this is what where neural networks really shine. So they don't take the raw features based on that. They don't make decisions. They first combine them in certain ways, which we are not directly aware of. So here I have explicitly declared that affordability is one thing, awareness is another, perceived quality is another, and so on. But you're not going to be always like, it would not be easier for you to always come up with these features yourself, which would be impacting the output probability. There would be cases which you wouldn't know anything about the problem. You just know that this is my input, this is my output, and you don't know if we combine feature number one with feature number three or feature number four, it would come up with some. It would be more useful. You don't know that. What we want to do is to, to hand over this task to the algorithm itself so that it can internally combine them in certain ways, which would come up with some really quality features impacting the output probability. And that's what neural networks exactly excel at. Any questions?
Great.
I don't have any questions for now.
Great. So this is kind of the intuition behind why a neural network usually excel. But of course, this is just one explanation. There could be thousands other things that a neural network is doing, which is not even visible to us, which could be impacting the output. But let me now introduce how does neural network tend to do this thing, this combination of features, um, to in order to produce an output. So let me provide you a formal mathematical definition of a neural network. Okay, so let's take an example case where we have features, let's call them x1, x2, and x3. So what a neural network does is it takes a particular feature it assigns a weight to it. It does it for all the features. So this x went outside this circle that I've drawn, but this is what happens. That looks funny. Let me redraw this thing. Okay. What simply happens is we take the weights assigned to each feature, we multiply them with the particular feature itself, and then we sum them all. And once we do that, we then apply what is called an activation function. So an activation function is applied on it, and that's how a single perceptron produces an output. So this is visually. If we write this equation, this would look something like this. Plus b, of course, I forgot about the b here, the bias term, and then an activation function is applied on it, and that's how it produces an output. This is the output of a single neuron. Now, when you look at it, you would immediately recognize that this is very similar to what we have been doing earlier. So we were taking, so if you recall the linear regression, we were taking a feature, we were multiplying it with a weight, and then we were weighting the bias term. If you recall logistic regression, the only difference was we took the linear regression formula and then we applied a nonlinearity on it, which was the sigmoid function. That's exactly what's happening inside a perceptron. So you can consider a perceptron as a logistic unit. This is the exactly the same thing. You can consider this as a logistic regression. So if this is a logistic regression, then what is a neural network? Well, a neural network is when you combine multiple logistic units together. So we take this and we replicate this thing. So let's take an example where we have multiple such logistic units. So previously, in order to produce an output, this is what a logistic unit was doing. It was taking this portion and applying the sigmoid function. But now, in order to produce an output, we can do something like this. So we can take the inputs x1, x2, and x3, and instead of producing a single logistic unit here, we can produce two logistic units here. So these features are going to contribute to this first logistic unit with one set of weights, and these are the same features are then going to contribute to the second logistic unit with a different set of weights. So the let's call them Z, or what should I call them? Let's call them Y1, Y2, Y3. And of course, there's also always a bias term. So this is B2, and here is B1. Let's call it A1, and let's call it A2. So how is A1 produced? A1 is produced in this exact similar manner. So if I quickly write its equation, A1 is nothing but the summation of I starts from 1 goes up to 3 Wi xi plus b1. How is A2 going to be produced? A2 is going to be produced in exactly similar manner. The only thing is now the set of weights that are assigned to it are different. So we have yi xi plus b2. And then we take these two and assign different set of weights to them in order to produce an output. So let's call it C1 and C2. And there's a bias term, let's call it C, just C. So what happens here, let's call it Y hat. So the way Y hat is produced is that it takes the output from the previous two logistic units, assign them these weights, so it would be C1 A1 plus C2 A2 plus C, and then there's an activation function applied to it. So as you can see, input features are coming. We are first producing A1 and A2, and then we are combining A1 and A2 in order to produce the output. This could be a simple neural network where we take the raw input features, do not produce the decision directly from it. Instead, we have this layer here where we first combine these raw features into these two, and then we make use of those two in order to produce an output. So let's go back to the original intuition that I was talking about here. So instead of taking these features and producing the output directly, we said that it would be more better if we come up with these features because they would be more better in order to predict the probability if it's going to be a top seller or not. And if you look at this simple neural network, this is exactly what's happening. So this A1 could be, let's say, determining the affordability of the shirt. Forgive me for my spellings. I don't know how it spells. And then A2 could be looking for, let's say, the perceived quality. And if so, I've just put here these two units. We could put, let's say, 3 units. There could be A3 or maybe 4. This A3 could be looking for something else. A4 could be looking for something else. And you can add as many units as you want. And the more units you add, the more complex behavior this neural network would be able to model, because the more features, internal patterns it would be recognizing, and then making use of those patterns, it would be a lot easier for this model, for this neural network, to come up with models that can handle more complex data or more complex problems. Does this make sense?
Yes, it does. My question is it like similar to feature engineering? Like it does feature engineering on its own? Because we look for features that affect our output in feature engineering, right? And that's what the neural network is doing.
Exactly. This is feature engineering. The only thing is we are not doing it. We are
Right.
handing over the task to the neural network. So previously, what happened is that, let's say you are making use of a linear regression, or let's say another traditional learning algorithm like SVM. Um, what researchers would do is that they would look for handcrafted features. So just like I have given you here the example that we could be combining price and shipping cost to the affordability. Now these were handcrafted by researchers themselves. Another example would be combining, let's say, the height and width into the area. We know what an area is. We know that it's a useful feature, but we have designed it ourselves. We have handcrafted it. The beautiful thing about neural network is we don't have to do that. It would be looking for those features intrinsically. We don't have to explicitly declare them. And by making use of the internal feature engineering, it can make decisions which would be more informed and more accurate in problems which would be complex. And there could be
Right.
places where even explicit feature engineering would not be possible. You wouldn't even know if there is such a feature, um, but a neural network would know. It can spot those patterns and it can make use of them. That's the, I mean, that's the core reason behind combining these multiple layers, having these long lists of neurons, because we wanted to spot patterns, come up with complex relations, which is difficult for us to do by looking at it or by using our own knowledge.
All right.
Makes sense.
So I also have a question.
Hmm.
My question is, the features that it generates for us, can we like find a minute with them? For instance, you mentioned A1 or A2. So say we could like understand maybe A1 is for affordability or perceived quality or anything like that.
Victor, can you speak a bit louder?
Okay. So I was asking if we could have like a little bit of meaning to the features it generates for us automatically. Can we know maybe all right, this feature is probably related to affordability, or is it perceived quality or stuff like that?
Are you asking if it's possible to tell what features have been engineered after the model is trained? I couldn't completely
Yeah,
understand.
like
Mm.
Like, what if you want to like get like an information about what features it generated and
Yeah,
probably learn from it?
Okay, so we don't know that. Even if you train a neural network, it is making accurate decisions. There's nothing that it can tell you about what kind of features has determined. So it's not like if you look into this A1, you would immediately recognize, oh, this is affordability. That's not going to happen,
yeah,
and that's its weakness. That's one of its weakness. That's why neural networks are often given this name. These are black box algorithms. Why black box? Because you don't know what's happening inside. For simpler neural networks, like for one layer neural networks, you can still come up with some theories that this is what it is doing. You can spot, it can give you a little bit of hints about what is happening. But imagine a neural network with millions of parameters. There's no way you can take a look inside it and determine what it is doing. So that's one of its weakness, although they're very powerful decision makers. Uh, but how they arrive at their decisions, we don't know. And this is one of the criticism that happens on it. So earlier than, like back in the 80s, there were two major groups in AI. One were called the symbolic AI people, and another one is called this neural network people, or another technical term for it is distributed properties or distributed AI. Um, so the symbolic AI, they exactly does what we've been talking about. So they say that you have to like make these features yourself. Like you know what is affordability, what is awareness, what is perceived quality. If you construct an algorithm based on these features, which you know what they are, um, you can have a visibility inside this algorithm. You know what is happening. You know how it is arriving at its decision. You can clearly see it's combining price and shipping into the affordability and then making use of affordability to come up with an output decision. What a neural network does is you have lost that ability. So you don't know what is this A1 and why is it important for a neural network. And till around 2012, um, so this is something that I have heard from one of the non-symbolic AI people. They said that even if we would construct a neural network which would be making accurate decisions, if we would try to write a technical paper on it and submit it to a journal, they would quickly reject those papers just for a simple reason that they say, what is it doing? Like, how can you explain this thing? So if you cannot explain it, there's no place for it in the journal in the academia. But after that, the impressive performance of it convinced the symbolic people to to incorporate them, even though you don't know what is happening inside, but still they are very powerful decision makers, and there's no stopping them now. Anyways, so I think I've spent a lot of time talking about the generic stuff. Let me just formalize quickly, give them the technical name. So this is usually called an input layer. Uh, these are called hidden layers. So for this particular example, we have just a single hidden layer. So these are called hidden layer. But keep in mind that there could be thousands of hidden layers. So maybe after we come up with A1 and A2, we can then combine A1 and A2 into something called, let's say, K1 and K2, which could be some other units, combining those two. And then we can combine those two to create something else, and so on. So the more and more layers you try to add, the more deeper your architecture becomes. And that's where the term deep learning comes from, that you have the network becomes so huge, you have so many hidden layers. Um, like that's where the deep learning terms come from. And this is then the output layer, right? Okay, so let's talk about what is a forward pass. A forward pass is nothing but, a forward propagation is nothing but making a decision from a neural network. So let me draw a clean neural network here. with just, let's say, two hidden units and then an output unit. So as you saw that in order to produce A1, we have one set of weights for it, and in order to calculate A2, we have a different set of weights. Let's call them Y1, Y2, Y3, and then there's this bias term. Let's call it B2. And then in order to produce, let's say, Y hat, which is the output, um, let's call them C1, C2, and C. So how this neural network produces an output? Well, it takes these weights, um, mul- take these features, multiply them x1 with w1, x2 with w2, x3 with w3, add this bias term, and apply a nonlinear activation. We'll talk about activation functions. Apply an activation function, and that's how A1 is generated or calculated. For A2, we take the same features, x1 multiplied with y1, x2 with y2, x3 with y3, apply an activation function on it, add the bias term, and then apply activation function. That's how we produce A2. And then in order to produce y hat, we take A1 multiplied with C1, A2 multiplied with C2, and add a bias term C to it, and then again apply an activation function. And that's how y hat is generated. This is a neural network where we have an input layer, one hidden layer, and an output layer. And that's how an output is generated. So if you know these weights, these trained weights, you can make the prediction from this algorithm in this way. And this is called a forward propagation or forward pass.
Yeah.
Does this make sense?
Yep.
Victor and Burhan, can you explain what's the difference between a weight and a bias?
I think it just from the formula, the weight is multiplied by like the input,
Hmm.
and you add the bias to it.
Yeah, that's right.
Great. Let's talk
I,
about these activation. Uh-huh.
I think bias is like maybe adjustment factor, and then weights is like association with the associated factors.
Yeah. So you're right. We take weights, multiply them with the features. So it controls how much that feature is contributing to the output. But once you account for all the features, the bias term shifts the entire activation
Right.
um, to, to some value. So it's not
Mm,
related to any feature, but it is there. That quantity is present in the relation.
right.
What, and when people talk about the weights of the model, Naveed, sometimes they say weights, but don't they really mean the weights and the biases?
Yeah, so weights are like they include both. So when someone called the weights of a model, you automatically understand that they
Yeah.
mean weights and biases. If you don't have biases, then you cannot produce an output.
Yeah.
Okay, let's talk about what is happening.
Microsoft Windows needs to update.
Let's talk about the activation function. So, has anyone thought why is there the need of an activation function?
I'm not sure.
Okay, so the term activation, it also, I think it comes from the terminologies associated with the biological neural networks. So the way neurologists study brain is like, um, if you are looking at something, suppose they are testing your visual cortex or something, like when you're looking into something, what happens inside the brain. So when they study the brain, they see that some regions of brain or neurons in those regions fire and some regions stay quiet. So how do they detect? Of course, neurons communicate with each other using electrical impulses. So when the electrical activity is higher in a particular region, they say that these neurons are activated more, and the rest are not activated. When you are looking at, let's say, a beautiful girl or something, particular activations, neurons in your brain
Right.
related to that phenomena that you are discussing. they they fire more. So this term comes from there. Now, what happens is when we are, let's say, computing the A1 and A2, maybe for certain examples, so suppose this neural network was producing, we have trained it to predict, let's say, if it's something, let's say, between a cat and a dog, or if it's a dog or not, um, or let's say if it's a cat or a dog. So let's say we feed it an image of a cat. You'd see that certain units here, let's like we just have two here, but consider there are 100. Certain of them would fire more. Fire means their values would be higher than others. And what controls that? The activation functions control that. So once you have this input coming to this A1, after you apply the activation, the value is going to be either a higher value or lower value. If it's higher value, it means that unit is activated more. And if it is a lower value, it means it's not activated that much. So this term, I think, comes from there, although I haven't studied literature on it where the term activation comes from, but I think I've heard it somewhere. But the question is, why do we need activation functions? Cannot can a neural network not work without an activation function? Well, it turns out if you try to remove the activation functions, these non-linear functions, um, the neural network just boils down to simple linear regression. So let me quickly give you an example. And James, I think you won't have time for the code today.
We can see.
So let's see. Let's take a simple neural network. We just have single feature X. We feed it, um, and there's just one hidden layer with one unit, and then there's, let's say, another hidden layer again with one unit, and then there's an output. This is the simplest neural network that you can think of. Um, so how is A1 produced? Well, A1 is produced by taking X1 or just X because we have one feature multiplying with the weight W and then adding a bias term B. Okay. How is A2 produced? Well, A2 takes the previous output, which is A1, multiplied with its own weight. So let's call it W1 and B1, and let's call it W2 and B2, right? So it's taking just simply the previous output, multiplying it with another weight, and adding another bias. This makes sense, right?
Yes, it does, but can you like go over it again? I missed something.
Okay. So we have a neural network with, let's say, two hidden layers, and each hidden layer is having just one unit or one neuron or
Yeah.
one logistic unit. So this is our input feature. How is the first logistic unit computed? Well, we just simply take our feature, which is X, multiply it with its corresponding weight. Remember these weights?
Hmm.
So that is W1 multiplied with X, and then we add a spice term, which is the B term, B1. That's how we produce an A1. You would ask me where's the activation function? Well, I'm trying to build a case of for why we are using activation function. So currently, let's see, we don't use any activation function. That's how A1 is generated. And let's
Right.
say, how is A2 generated? Well, A2 just simply takes the output from the previous layer, which is this, multiplied with another set of weights. So this is A1 gets multiplied with W2, and there's a bias B2 added to it, and that's how it produces an A2, right? And again, I'm not applying an activation function because that's what I'm doing. I'm trying to build a case for why we use activation function. Till this point, you are clear, right,
Yep.
Victor,
Yes, I'm clear.
James?
Yep.
Great. So let's see. Let's take the value for A1 and plug it inside this A2 and see what happens. So A2 is just W2 times W1 X plus B1 plus B2, right? I'm just taking that A1, plugging it inside this equation. And let's just multiply this W2. So this becomes W2 W1 X plus this
W2B1
W2 B1
plus B2.
plus B2. Now let's see, W2 and W1, both are just some scalars, some values. And if you
Right.
multiply two scalars together, this is nothing but just another scalar. Let's call it W.
Mm.
And W2 B1 plus B2, all these are scalars. So combining them just makes another scalar. Let's call it B. So what this boils down to, A2 just simply becomes Wx plus B. Now you
Right.
remember what was this? This was just a simple linear regression, if you remember.
Mm-hmm.
Yeah.
So what it tells you that if you don't use an activation function, your neural network boils down to just a simple linear regression. In other words, uh, a linear function, like when you combine multiple linear functions together, the result is also a linear function. So you cannot get something complicated out of combining linear functions. And as you can clearly see, these are just linear functions. A1 is just taking a scalar multiplying with x, adding a b, a linear function, another linear function. And a linear function of a linear function is a linear function. This comes from algebra, the basic linear algebra. Does this make
Right.
sense?
Mm-hmm.
Yes, it does.
So that's why we have to introduce some non-linearity into it. Otherwise, our neural network, no matter how many hidden layers you use, no matter how many units inside a hidden layer you use, all of them would be nothing but just simply a linear regression
Yeah.
by following this derivation here. So that's one explanation for it. Another general explanation for it would be we are looking for something complex, not linearly dependent on each other. In order to model something complex, we have to introduce nonlinearity into the equation, and that's where activation functions play their role. Okay,
Yeah.
perfect. So let's finally talk about, not finally because we have back propagation as well to talk about. Are you with me? Are you feeling fresh or asleep already?
Always
Yeah.
fresh.
Turns on his camera to say that.
Yeah.
Okay, the question is, okay, we have a neural network that looks like this, um, which makes a decision using forward propagation. We have activation functions. Everything is beautiful so far. But the real question is, how do we train such a thing? Because previously we saw that if you take a linear regression, the way we train it is we just simply take it, and apply gradient descent on it. Well, applying gradient descent on a linear regression or logistic regression was super easy because we had an equation. We just have to compute its derivative. Um, the equation was the cost function, and we have to compute its derivative. All the parameters were inside that equation. But in a neural network, the story is different. How is the story different? So let's take this as an example. Let's say we are using this neural network to do regression. And what is the activation function? Or sorry, the cost function for regression? Well, the cost function, if you recall, okay. So the cost function, if you recall, is j equals to 1 over n, where n is the total number of examples, summation I starts from 1 goes up to n, y hat minus y squared. This was the cost for linear regression, or sorry, regression, any regression. This y hat comes from our model. When the model was linear regression, which was nothing but wx plus b, it was super easy to take the derivative of the cost function with respect to, let's say, w. Why? Well, because this was a function of w. W was explicitly written here, and we can just simply take its derivative using the power rule of derivatives. But what happens is in a neural network is now this y hat is not explicitly defined. The way a neural network produces an output you saw is that it makes use of forward pass. So if I task you to, let's say, compute the derivative of this activation function with respect to, let's say, w1, this thing, how are you going to do that? Because y hat is now, uh, the way y hat is generated, I think I wrote the formula here somewhere, is that it is making use of A1 and A2, right?
Right.
And then A1 and A2 was defined here. So this is A1 and this is A2. What I'm simply trying to say here is this is not an explicit function for W1 and W2. So you cannot directly compute its derivative. We have implicit functions inside it. And that's why we are going to make use of something called the chain rule of derivatives. Has anyone heard this thing before?
Chain rule, yeah.
What is the chain rule?
We applied the derivative in chain. It's like mostly used in trigonometric functions.
It is used inside trigonometric functions and non-trigonometric functions equally. So
Mm.
let's see. Let's take an example function. So let's say we have f of z equals z squared plus 3, and then we have z of x equals x cubed. And
Mm.
I task you to find the derivative of f of z with respect to x. Can you do that?
Yep.
We cannot explicitly do that because, as you can see, f is a function of z, and I'm asking you to compute its derivative with respect to x. Well, this is not a function of x. However, z is a function of x. So what I can do is I can compute the derivative of z with respect to x. So I can do this thing, d of z with d of x, and then since f is a function of z, I can compute the derivative of f with respect to z. I can compute these two derivatives, but I cannot directly compute the derivative of f with respect to x. So that's where chain
Yeah.
rule comes into play. Chain rule says that if in order to compute the derivative of f with respect to x, you first need to compute the derivative of f with respect to z, and then the derivative of z with respect to
Z with
x.
respect to x.
So you can consider these two cancels out, and you are left with the derivative of f with respect to x, right?
Yep.
This is chain rule, standard chain rule. This is exactly what we are going to be making use of in our example here, because y hat is not directly a function of w. Y hat is a function of a1 and a2, and then a1 is a function of w1, which we are interested in. So in order to do that, we can do something like this. So in order to, let me write it here, in order to compute the derivative of j, which is a cost function with respect to w1, what I can do is I can first compute the derivative of j with respect to, let's say, um, y hat. I can then compute the derivative of y hat with respect to a2, y a2. Sorry, this should be a1. And then I can take the derivative of a1 with respect to w1. So you can see here, I'm starting from here, taking the, so j is a function of y hat. I'm taking the derivative of j with respect to y hat. Y hat is a function of a1. It's also a function of a2, but I'm deliberately ignoring that because it becomes super complex here. So I'm just trying to show you that we start from here, we compute the derivative of j with respect to y hat, then compute the derivative of y hat with respect to a1, and then compute the derivative of a1 with respect to w1. So that's how we reach. We start from the output layer, we propagate back to our network, and we reach at these weights. We do this for w1, we do this for w2, w3, y1, y2, y3, and all the weights that we have inside our network. That's how you reach at every single weight in order to compute the derivative of the cost function with respect to that particular weight. Are you following me,
Yep.
Yes.
Victor, James? You?
Yeah, the only thing I'm kind of wondering is what would happen if you tried to, like, I understand how the chain rule is working. What would happen if you tried to calculate the derivatives from the other end?
That would, yeah. So you can do that. So if you start, let's say, from the left side, first compute the derivative of a1 with respect to w1, and then compute the derivative of, let's say, y hat with respect to a1, and then compute the derivative of j with respect to y hat. um, the the problem appears in implementation. So you can do that in theory. You can do that using a paper. The problem appears when you are implementing these inside a computer. So inside a computer, like for instance, let's take TensorFlow. The way it computes these derivatives is using what is called a computational graph. And I won't have time to go into the details of it, but if you start from left to right, the complexity, like you would have to do calculations over and over and over again in order to do this for, let's say, W1, W2, W3, and so on. You would have to do more calculations if you start from left to right, go towards right. But if you start from right towards left, the amount of computations are greatly reduced because you would, once you compute the derivative of, let's say, y hat with a1, you can use that to do the computation for all of these together,
Yeah.
something like this. But of course, I'm not totally confident. I know this is true, but I don't know the exact implementation details of it. But what I'll give you the computational complexity. So it is shown that if you do this from left to right, the computational complexity is n times p. If you do it from right to left, which is what his backprop is doing, the computational complexity becomes n plus p.
Oh.
So n times p is way more than n plus p. Um, so that's why we don't do it using the other way around. And back in the days, people didn't know about backprop. Backprop came a lot more later than um, earlier. Like neural networks existed for long ago. People just didn't know how to train larger neural networks. When backprop came, it solved that problem, and that's why it excelled afterwards.
So N and P are the number of layers and the number of.
Well, I think I don't know that
Okay.
because I just know this relation that
Yeah.
it is n times p, but I'll have to check
That's
what exactly
interesting.
these numbers mean.
No, that's really interesting.
Great. So that's Backpass. I think if I talk more, you won't follow me further from here. But if you have any questions, I would love to answer them.
Okay.
No questions.
Is that a lot to take in?
Uh, you're saying something, James?
Oh, I was just asking everyone. Is that a lot to take in?
That's all right.
Absorbing it. Burhan, you've seen some of this before, right? In your because you've done
Mm-hmm.
an online course, right?
Yep.
How similar is it to what you already studied?
It's like I have done more in this course, and I didn't get enough time for that. But like, it's the approach is of obviously the same. But yeah,
Okay.
it's nice.
Okay.
Okay. Um, so to summarize the whole discussion, um, as you can clearly see, the idea stays the same. So we have what is called a hypothesis function for a model for neural networks. It is defined in this way. So we don't have a nice little equation just in the case of linear regression, logistic regression. We now have this thing. In order to produce an output from it, you'd have to do forward pass. And forward pass is first computing these hidden units, then combining them to produce something, um, to produce an output. um, so you produce an output using forward pass. Um, Once you produce an output, because initially all these weights would be randomly initialized, we need to come up with a way to train this neural network. The way we train it is the same old gradient descent algorithm. The only problem is because in a gradient descent, if I want to update, let's say W1, I'd have to take the previous value of W1 and take the derivative of the cost function with respect to W1, and there's an learning rate with it. So the only problem is now this J is not explicitly defined in terms of W1, W2, and 3. These are all implicitly defined. In order to compute those derivatives, you make use of chain rules. Um, and, and we talked about how a chain rule works. So you go back inside your network, you do backward pass to compute the gradients or the derivatives of the cost function with respect to every single weight that appears inside your network. And then you update all of those weights using this gradient descent equation, and you do this iteratively, and gradually the loss of your model is going down. The loss stays the same. If it's a regression task, you make use of MSE. If it is a classification task, you make use of the cross entropy loss. So those things remain the same. The only difference appears in the model itself now. And
Fair
that's all.
enough.
Naveed, it's 9:09.
So yeah, I think James, you'd have to. You can proceed with the code if you want, if the guys are still fresh. But I think I'll have to leave.
Yeah, we don't want to make you late or hungry. um, cool. Yeah, what do you guys think about going another 10, 15 minutes so you can actually do some coding?
I don't mind.
I'm up for it.
Okay.
Okay, so I'll see you guys then.
Thanks a lot,
All
Naveed.
right.
This was an
Yeah.
See ya.
awesome
Bye, David.
session.
Goodbye.
See ya.
Take care.
Okay. Cool.
Hmm.
Yep.
So, are you ready to create a neural network?
Let's go.
What kind of things would you like to train a neural network on?
Hmm.
I won't mind
Probably.
seeing how it
Yeah,
performs
yeah.
on the Titanic.
What did you say?
I won't mind to see how the neural network performs on the Titanic data set.
It's a, the sound is like a little bit off. What was the last?
The Titanic data set.
Which data set? The Titanic one. Oh yeah. So
Yeah.
so yeah, actually
That's,
that's an option. That's an option. What about you, Burhan?
I'll have a look because it can be used on complicated data sets. So I'll probably choose something that is not really obvious to uh, normally obvious. Let's see what the neural network does with it.
Yeah, yeah, exactly. So what we've
Mm.
done so far, kind of, um, it works if the outcome is a little bit obvious. You know,
Yeah.
the regression you can see just by plotting a line through the data if it's going to work, and then logistic
Hmm.
regression, you can see if things are sort of clustered into different groups.
Right.
So the neural network things are you'll get a lot of like unexpected outcomes or something non-obvious. So this is the example that we're going to go through today. There's actually two examples because we've done regression and classification. So what we
Mm.
wanted to do was give you an example of how to do the exact same thing for both, um, but using a neural network instead. But I think for today, it probably will suffice to just go through a regression model.
Sure.
So this is the code to apply a neural network to the house pricing problem, which we did in the first lesson.
Hmm.
And Burhan, can you just remind me what did we do? What was the purpose of training that model?
Yeah, it was to we used square feet and we had the correlations and stuff to predict the prices.
Yeah, so we had all of this data about different houses,
Mm-hmm.
um, the number of rooms, whether it's on the waterfront, how big is the house,
Yeah.
and the example we did was a linear regression between the square foot in size of the house
Mm-hmm.
of the area, and then the price.
Yep.
So obviously it gets more expensive. And then there's also an example. I don't know if I showed it to you where we do it with all of the columns, and that's also on the same assignment page where
Yeah, it
we
was
combine all of
we
them.
did for multivariate.
Yeah. So when we're going to do this train a neural network for the same task,
Mm-hmm.
the preparation is obviously the same.
Right.
Um, using pandas and NumPy um, to process the data, and we want to remove any features that we don't want to use. And I think you'll remember that when we were doing multivariate, we wanted to standardize the data
Right.
uh, by subtracting the mean and dividing by the standard deviation for all of the items in the data set. We
Mm-hmm.
do the train test split, and so we have 21,000 data points with 18 features. Now, before we used, do you remember which Python library we were using before?
Scikit.
Scikit-learn.
Yeah, scikit-learn. And
Mm-hmm.
so we're going to use TensorFlow and Keras.
Right.
Have you heard of these two before?
Yeah, I have TensorFlow.
Yeah. So Keras is part of TensorFlow, and it's basically like a nice interface or wrapper around a lot of the more low-level stuff that TensorFlow does. But
Mm-hmm.
basically, what it does is Keras has the basic architecture of a neural network built into it. So we don't need to go in and define stuff that we already know, like the loss function, um, or define the actual operations
Right.
of the neural network. All we need to do is give it a list of layers, and the properties of those layers. So if we would do this with TensorFlow, we'd actually be writing like, oh, the the layer two is the sum of the weights and the biases, and layer one and the activation function. But in Keras, you can literally just put in here, we want one layer, two layers, and this is the activation function we want. It's called ReLU, and this is the shape of the input. So there's 18 inputs to this model, as we know, and then the number of perceptrons for each layer. So here we have 10 in the first layer, then we have a second layer, the same activation function, and then do you know what we're doing here? In this
I think
last
we imagined the 20 previous layers into a single output.
exactly.
We're condensing it.
Exactly. So all of those perceptrons, just a line coming out of all of them, just going into one final
Mm-hmm.
perceptron. And the compile,
Also,
yeah,
quick
yeah.
question. Why 1020 specifically?
Oh, no specific reason, and that's going to be a part of the first part of your assignment. Is can you actually the first thing that actually I want to ask you to do with this code is to make a
Mm-hmm.
copy of it and then see if you can make it better.
Right.
Um, it's not specific. There's no specific justification. Oftentimes, it's just based on what previous things worked well in the past.
Fair enough.
Um, Although there are like a lot of cases where you would, mm, yeah, actually, it is a bit interesting to go from 18 to 10 to 20. Mm, but yeah, actually, I can't say any more than that. So this summary method just gives us a summary of the shapes.
Mm-hmm.
Um, so actually, a question for you both: how would you go about? So like this number 190, 220, this is the number of parameters, right?
Right.
Um, how would you go about calculating how many parameters there are, right? Because it's obviously not 10 times a number, right? So
Mm.
how do you get to the number of parameters in a layer?
A bit
By
tricky.
different weights.
Mm-hmm.
Sure.
So what types of parameters do we have in the neural network?
Weights.
Uh-huh.
We have weights and we
Bias.
have the bias.
Yeah, exactly. So
Mm-hmm.
so here, if we look at the last layer, it's actually kind of obvious because it's 21, right?
Mm-hmm.
So in the layer before the last one, there were 20 perceptrons. So there's going to be
Right.
20 inputs, And then because there's only one perceptron here, there's only going to be one bias, if that makes sense.
Fair enough.
So
So
it's
it's
20.
like 20 biases for the above one.
Exactly. So this one will be 20 plus 1.
Mm-hmm.
And then here it should be, because these are interconnected, these
Right.
these perceptrons, these ones, it should be 10 times 20 plus 20 by 10 times 20 weights plus 20 biases. Then you get to 220.
Fair enough.
And then for this one, for the first layer, you have 19 inputs. So times 10 is, or no, that doesn't make sense. You'd probably have 18 inputs, right? Times 10 is 180 plus 10, 180 weights plus 10 biases. Then you get
Yeah.
190 first. So you sum up these three, and then you get the number of trainable parameters in the whole model. So that's 431 trainable parameters in the model. Ignore non-trainable. And then, so we run the model compile. All that does is it sets up the model. I think it may put in some random initial parameters. Doesn't do any training. It just sets up the model architecture. Now we run fit. This part should be pretty similar from the linear and the logistic regressions. Number of epochs. How many times we train it in order to decrease the loss and improve the accuracy.
Right.
And this is the validation data from the train test split. So if I would run this right now, it would go 1, 2, 3, 4, 5, and we'd be sitting here for a little while.
So like it all depends upon the computational power, right? Like
Of course,
how
yeah,
much epochs do I want?
of course, yeah. And here in Colab we have, maybe is it here? Yeah, under notebook settings,
But you have the GPU.
you have some different options, right? So T4 GPU is the GPU that is Google has invented.
Right.
Or is that TPU? I'm thinking of TPU. Actually, I'm not sure what a T4 is. That's NVIDIA. Okay. Yeah. So I was thinking of the TPU. The TPU is that's a tensor processing unit.
Interesting.
And that's an ASIC developed by Google. So we can actually switch over to the TPU for maybe better performance on a neural network. That might be something to try. And then the A100s, those are the ones in high demand. But yeah, as you're saying, all depends. So after all of that is done, what you should be able to see while you're running it, a high loss initially.
Yeah.
The loss
It
is going to
keeps. Yeah, it keeps lowering.
and so we have the loss on all of the data, and then we have on the training data, and then the loss on the testing data. And it should go down, and at some point, it's going to stop going down so much, right?
Yeah.
At some point, it should plateau a bit. So it's going down, it's going down. Okay, now we've kind of getting slower. It's
Yeah. Yeah.
So now it's almost plateaued here. So you'll see that as you're watching it over time. And then we can plot that. And this is what it looks like. So here we're really just, yeah.
Not much happening.
Yeah. And this calculates this step here will run the model on all of our test data. So we can then calculate the root mean squared error for the whole test data set. And if we want to go back to, our linear regression model, or I'd rather let's do that doesn't make sense to compare. If we go back to the multivariate linear regression,
Yeah.
And we look at the root mean square error we were getting there, that was about 198.
Right.
So and then for this one, 185. So
Cool.
first task for you all is like, now obviously like don't spend hours because it's gonna take some time to run it, but it's
Yeah.
like, can you improve that, right?
Mm-hmm.
How low can you get this? And if you will add, I mean, you can change this architecture here, right? So that's the first question. Don't spend an hour on that, just mess around with it.
Mm-hmm.
um, and then the second question, the second task that we'll go over on Tuesday, is going to be, take an existing thing that you've done, for linear regression or logistic regression,
Right.
and then do it again,
With neural networks.
using a neural network,
Okay.
and it better be more accurate.
Yeah.
so so yeah, that's the code for how to train a neural network using TensorFlow and Keras.
Thank you.
Have you done this before, Burhan?
Thank you.
Nope. Non-neural networks.
Okay, cool. Yeah, then this should be super fun.
Yeah.
So it's all up there on the GitHub, and yeah, Tuesday we'll go over it again.
All right.
Sounds good.
Awesome. Thanks for today.
Yeah,
Yeah.
thank
Thank
you.
you.
All right, have a good weekend.
You too.
Yeah. See you guys next
Take
time.
care.
See
Bye.
you. Bye.
Bye.